This is Lecture 3 of Module 8 from the book Problem Solving Guide for Mechanics and Thermodynamics. The subject is angular momentum and rotational kinetic energy. The subject of the previous lecture was moment of inertia. Here we're going to use our understanding of moment of inertia to solve problems with rotational energy and angular momentum. So here's the first problem. Similar to the smokestack of the previous lecture, we have a mass M and length L rod hinged at one end. The hinge turns without friction. The rod is released 30 degrees above the horizontal. So we're holding it here and we let it go. What's the angular speed omega when it's horizontal? Just before it hits the surface. The initial energy is all gravitational potential. So we have to get the height of the center of mass. It is right here. That's L over 2, half the length of the rod. And the height is L over 2 times sine 30, the opposite side. So the initial gravitational potential is mgh. H is L over 2 sine 30. When the rod's horizontal, all the energy is in rotational kinetic. It's pure rotation. There's no translation. This is 1/2 I omega squared. We don't know the moment of inertia of a rod about an end. Well, I do, but let's derive it. We need the moment of inertia of a rod about an end. So the kinetic energy of this rod is the sum of the kinetic energies of all the dm's along the rod. So this v is the speed of that dm, and we're going to sum them all up. The dm is simply the total mass divided by the total length times the dr, the length of the little piece, the length of the infinitesimal piece. Right here, here's a good example of a dr. This dr is really thin. It is mass dm, and it's r away from the axis of rotation. The speed of the mass dm depends on how far it is away. The farther it is away, the faster it's going to be moving. The function is omega r, so that's the speed. So we now have 1/2 mv squared written as 1/2 m over L dr, that's dm, and v is omega r. So now we have everything in terms of r and some constants. This is an integral we can do. You have to think about the limits. dr, what's the range of dr? dr is really small. What's the range of r? R goes from 0 away all the way up to L away. So those are the limits of the integral. And we get r squared dr is r cubed over 3. Put the limits in, we get this. This is the kinetic energy of a rod of mass L, mass M, length L, rotating with angular speed omega. That's the kinetic energy. We can't use 1/2 mv squared because they're moving different speeds. We got to integrate. To get the moment of inertia, we set it equal to the general equation for rotational kinetic energy. We have this specific example of kinetic energy, a rod about an end. The general formula is 1/2 I omega squared. So we can pull the I out from this. We cancel the omegas, and we get that I is 1/3 ml squared. Moment of inertia of a rod about an end, 1/3 ml squared. So now we can use conservation of energy to get the final energy. We know the initial energy. The final energy is just the rotational kinetic energy, 1/6 ml squared omega squared. We just derived that. We can set these equal, and we can solve for omega. The m's cancel. Doesn't matter how heavy the mass is as far as the speed. 3g over 2l. So g is meters per second squared. L is meters, so this is 1/second squared. Take the square root, 1/seconds. That's omega. Let's see, what if the rod was 1 meter long? That would be 30 over 20, which is, no, 30 over 2, which is 15. Square root of 15 is 4. It's about 4 radians per second, a little bit more than 1 revolution per second. If this was a meter long, you dropped it at 30 degrees. Try this next time you're in the physics lab and see what you get. So this equation, this kinematic equation, is no good here. We can't use it because the alpha is not constant. The angular acceleration is caused by the torque. The torque is mg, the perpendicular distance mg is away from the hinge, and that is increasing as the rod falls. So the angular acceleration is increasing, so those equations are out the window. Before we tackle one conserving angular momentum, let's go over a few concepts of angular momentum. It's a rotational counterpart for linear momentum. Linear momentum is mv. So the angular momentum is I for the mass and omega for the speed. And use L for that. Angular momentum has different units from linear momentum. This is crucial to understand this. You can't transfer angular momentum to linear momentum. They're different things, even though they're both momenta. And we can see that the units are different in a second. They are conserved independently. It doesn't replace them. They're both conserved. When we do angular momentum problems, there's often a point mass colliding with a wheel, a rod, or something. So we have to know the moment of inertia of a point mass. And you probably know it already. Well, let's think about it the same way we thought about the other ones. The kinetic energy of rotation of a rotating body is 1/2 I omega squared. That's the general formula. For a point mass, we're going to consider a mass rotating in a circle on a string. It could be a planet orbiting a sun or something like that. It's a mass going in a circle, a small mass. It's going at speed v. The distance r away. Radius of the circle's r. What's the kinetic energy of the point mass? It's 1/2 mv squared. It's the same thing we did before. The speed is omega r. This makes the kinetic energy 1/2 mr squared omega squared. So now we can set this equal to that. And we see that I is just mr squared. The 1/2, so there, the omega's there, I is just mr squared. The moment of inertia of a point mass is mr squared, but you know that already. It's just like a hoop. All of the mass is r away. If all of the mass is r away, the moment of inertia is mr squared. So the angular momentum of point mass, I omega, is mr squared omega. Now we usually use v's for point masses. So let's put the v in. Instead of omega, we're going to put in v over r for omega, and we get mvr. So here it's obvious that the units of angular momentum are different, because there's an r in there. Linear momentum is just mv, angular momentum is mvr. R is the perpendicular distance away from the point of rotation. V and r have to be perpendicular. Just like when you do force times distance with torque. One of them has to be perpendicular to the other. So before we tackle a problem in angular momentum, let's consider some of the many examples of conservation of angular momentum in real life. So high diving and skating, just had the Olympics this year. Also gymnastics. The principle of conservation of angular momentum is clearly demonstrated. The equation for conservation of angular momentum that's relevant here is I initial omega initial is I final omega final. So if you want to change your omega without a torque, you need to change your I. Somebody going off a high dive is not going to have any torques on them, spinning them. So the way to increase your omega is to decrease your I. And the way to decrease your I is tuck all your mass close to the middle. So when somebody's going off a high dive, they want to rotate fast, they tuck into they get their R as small as they possibly can. Same thing with a gymnast. When an ice skater wants to increase the rotation rate, she reduces her moment of inertia by bringing her legs and arms in. So that's a camel spin, so her leg's way out there. The skate's heavy. It's got a big moment of inertia if it's far away. And she goes even tighter here, and of course spins around a lot faster because her moment of inertia is reduced. The principle of conservation of angular momentum can also be used to maintain an axis. When you say conservation, it stays the same. So you throw a football, you spin it to give it some angular momentum and prevent it from wobbling. When a bullet is shot, there's grooves along the inside of the barrel so it doesn't tumble. So here's a look down the barrel of a rifle. And you can see the grooves are sort of spiraling the bullet out so it spins. Gives it a little twist, just like a football when you throw it. The term rifle comes from the French rifler, which means to graze or scratch. So the name rifle came from this process of rifling the barrel of the gun. Gyroscopes with a lot of angular momentum, spinning really fast, mounted in gimbal rings, are used on aircraft for information such as the pitch, the bank, the yaw, the heading, because gyroscopes will stay in the same orientation if they're mounted in a gimbal mount. So here's a gimbal mount, and you can see how the gimbal mount works. The gyroscope is free to do whatever it wants. So if the plane moves, the gyroscope will stay in the same orientation. So if the plane's nose dips, the gyroscope's going to stay in the same orientation so the plane knows how much the nose is dipping and how to recover. There's a little instrument panel that tells you all of that. They're also used to stabilize movie cameras. So here's a gyroscopically stable movie camera. And if you hold on here, these two handles, the picture you get is going to be very stable because there's a gyroscope in there keeping it. If you held onto the camera with your hands without the gyroscope, any jittering your hands did would be reflected in the video. Also, they're used to counteract roll of large ships in rough seas. This World War I transport, the USS Henderson, had two 25-ton, 9-foot diameter flywheels mounted near the center of the ship that they would activate in rough seas to counteract the rolling. Elliptical orbits, satellites going around planets, planets going around suns, asteroids going around planets. This concept's useful. MV perpendicular R is constant throughout the whole orbit of the satellite. MVR of the satellite is constant. Here's a planet. If you're close to the planet, you can have a high speed. R is small, V is big. If you're far away from the planet, you can have a small v. MVR perpendicular is the same all the way around. Helicopters have a tail rotor. It provides stability when the angular momentum of the main rotor is changed. So here's a helicopter. There's the tail rotor. What would happen if the angular speed of the main rotor was changed but the tail rotor was out? Angular momentum of the helicopter is conserved. So if you try to spin the blades faster this way, the whole helicopter is going to spin the other way. So the helicopter is going to spin in the opposite direction. The tail rotor prevents that. Heavy lift helicopters sometimes don't have a tail rotor. They just have two main rotors. How is that stable? What's up with that? Think about it. Well, the blades rotate at the same speed in opposite directions. So the total angular momentum of the two blades is 0. Then you don't have to worry. Formula One race cars have kinetic energy recovery braking systems, KERS. It's a big, heavy carbon fiber flywheel. Note that there's not so much mass in the middle. It's all on the outside because that's where it matters. To brake, instead of using heat, you connect the wheels with this flywheel that's inside the car. And this flywheel has a lot of inertia. So the car slows down fast when you connect the wheels with the flywheel. But now you have a spinning flywheel that has a bunch of kinetic energy. So you come out of the turn, which you slow down for, and now you connect this flywheel back up to the wheels, and it gives back the energy. Conventional braking just produces heat, and that's wasted. So we can store the kinetic energy temporarily in the flywheel and then get it back when you need it. Teslas and other electronic cars have regenerative braking systems. When you take your foot off the gas, not really a gas pedal in an electric car, the kinetic energy of the car is used as a generator to charge the battery. And you can see this on the instrument panel in a Tesla. This is normally this is the power side of the speedometer. And it's normally amber when it's up here because you're using power. This person was going 209 kilometers per hour and took their foot off the gas quickly. And when you do that, the car slows down very quickly, and this green indicates the battery's charging. So you're really charging the battery here. Same thing happens when you go downhill. If you go downhill, it's a steep hill. You go into the mountains and you're going downhill for a long time, you're going to charge the battery in your Tesla. The driver that's used to this type of braking system only uses the brake pedal in emergencies. So to slow down the car, you don't put your foot on the brake, you take your foot off the gas and put that energy back into the battery. Brakes last a long time in the Tesla because you almost never use them. Okay, let's do a physics problem using concept of conservation of angular momentum. You have a 300-gram meter stick suspended from one end. A 30-gram lump of clay hits the stick 20 centimeters from the bottom at a speed of 10 meters per second and sticks to it. And then, as a result, the meter stick swings up. It's suspended from one end. What angle does it swing through? So here's a diagram. Here's the clay. It's going to hit at 80 centimeters, stick to the meter stick, and then the whole thing's going to swing up some angle and stop and then oscillate. We want to know the maximum angle. The linear momentum, mv, of the meter stick and clay system is not conserved because there's a force here. In order to conserve linear momentum, you have to just lie this meter stick on a Iraqi table or something. You can't have any external forces. This pivot is an external force. But angular momentum is conserved about the pivot, only about the pivot. The condition for the conservation of angular momentum is that no external torques are present. To conserve linear momentum, it's no external forces. To conserve angular momentum, no external torques, and there are no external torques about the pivot because the pivot acts here and it doesn't exert a torque because its distance away is 0. So we can conserve angular momentum about the pivot. We also know that thermal energy is going to be generated because this is completely inelastic. It sticks to it. So we can't say the kinetic energy of this thing is equal to the gravitational potential of the meter stick and clay when it's up in the air over here, because there's thermal energy generated. The initial angular momentum about the pivot is only from the clay. It's mvr. Right? The perpendicular distance is 80 centimeters. It's going this way, 10 meters per second, has a mass of 30 grams. There's the initial angular momentum about the pivot. Just after the collision, the final angular momentum is I omega, where I is the rod and the clay, the meter stick and the clay. The mode of inertia of the combination, we have a rod about an end, which we just calculated, right? 1/3 ml squared. So there's the rod, 1/3 m, mass of the rod, that's given. 1 meter long, that's the mass of the clay. 0.8 meters is the position. It's mr squared. Remember, it's a point mass. So it's just mr squared. The clay is 80, all of the clay is 80 centimeters away. We add that up, we get 119.2 grams meter squared for the moment of inertia of the clay and meter stick. We can now set the initial angular momentum here equal to the final angular momentum and calculate omega just after the collision. So that's the initial, that's the final. Divide by 119.2 grams meters squared, and we get 2.01 radians per second. Now let's put in the final snapshot. So the clay hits, this thing takes off with an angular velocity of 2.01 radians per second. And it's going to stop because of gravity. Gravity is going to eventually stop it at this theta max. We have to calculate theta max. This second or third snapshot, if you will. So the first snapshot is just this guy moving. The second snapshot is the clay stuck to the meter stick and the meter stick going up at 2.01 radians per second. And the final one is everything's at rest, nothing's moving, and it's up in the air at some angle, theta max. The meter stick itself, using the center of mass, it's a half a meter, 1 minus cosine theta max, and the clay went up 0.8 meters times 1 minus cosine theta max. To see where this comes from, I put some distances on here. That's the change in height of the clay. The clay went up this much. Started at this level, went up to that level. This is 0.8 meters. That's where the clay is. That's the hypotenuse. This is 0.8 meters cosine theta max. So the whole thing, when it's straight up, is 0.8 meters. So the height of the clay is 0.8 meters minus 0.8 meters cosine theta max. We factor out the 0.8 meters and get 0.8 meters times 1 minus cosine theta max. Take your time, make sure you understand that calculation. So there's the height of the clay, the final height of the clay. The increase in gravitational potential energy is mgh for the meter stick, mgh for the clay. That reduces to this. 1 point, you can factor out the 1 minus cosine theta max, and you can set this equal to the energy just after the collision, 1/2 I omega squared. Moment of inertia of the clay plus the meter stick, angular speed of the meter stick after the collision. It's that much, so we can solve for theta max by setting those equal. No thermal energy is generated during the swing. The thermal energy is generated during the collision. So we avoided the collision by getting the clay and meter stick speed, angular speed, just after the collision. So the gravitational potential energy here equals the kinetic energy at the bottom, which is 0.241 joules. And we can solve for 1 minus cosine theta max, take the arc cosine of both sides, and we get 30.5 degrees. That's the maximum angle. The initial kinetic energy of the clay, 1/2 mv squared, was 0.375 joules. After the collision, there was 0.241 joules of kinetic energy, so 0.134 joules of thermal energy was generated in this inelastic collision between the clay and the meter stick. This module has a lot of concepts that are going to take a significant amount of time to wrap your head around, so do a lot of problems. Get to work.